Welcome! In this session, we'll explore problem number 92, reverse linked list 2. This is a classic linked list manipulation problem where we reverse a sublist within a given range. Let's break it down step by step and solve it efficiently. Stay tuned! In this problem, you are given the head of a singly linked list, along with two integers, left and right. These integers represent positions in the list, using one-based indexing. Your task is to reverse the nodes between these two positions, while leaving the rest of the list unchanged. The function should then return the head of this modified list. For the input format, you'll receive the head of the linked list, a list node object, and the two integers left and right. The output will also be the head of the updated linked list after performing the reversal. Let's consider some examples to clarify. In the first example, the input linked list is 1, 2, 3, 4, 5, with left equals 2 and right equals 4. This means we need to reverse the nodes from position 2 to position 4. After reversing, the updated linked list becomes 1, 4, 3, 2, 5. In the second example, the input linked list is 5, with left equals 1 and right equals 1. Since there is only one node in the list, and the range includes just this single node, no changes are made. The output remains 5. Here's another example. If the input linked list is 3, 5, with left equals 1 and right equals 2, we are asked to reverse the nodes from position 1 to position 2, which covers the entire list. After reversing, the updated linked list becomes 5, 3. This demonstrates how the function handles cases where the range includes all nodes. Now, looking at the constraints, the number of nodes in the list, n, is between 1 and 500. Each node's value lies between -500 and 500, and the indices left and right will always satisfy the condition 1 equals left equals right equals n. Let's examine some edge cases. If the linked list contains only one node, meaning n equals 1, the list remains unchanged regardless of the values of left and right, since there's nothing to reverse. Similarly, if left is equal to right, the range includes only one node, so no reversing is performed. On the other hand, if left is 1 and right is equal to n, the entire linked list is reversed. These cases highlight the importance of considering both small inputs and scenarios where the range spans the full list. To tackle the problem of reversing a sublist within a linked list, we need a strategy that carefully manipulates pointers while preserving the integrity of the list structure. The first approach we considered is the brute force method. The idea here is to extract the sublist defined by the left and right positions, reverse this extracted portion, and finally reconnect it to the rest of the list. The steps involve traversing the list to locate the boundaries, extracting the nodes between these positions, applying a standard reversal algorithm, and then reattaching the reversed portion back to the remaining nodes. While this approach is conceptually straightforward, it requires additional memory to temporarily store the sublist. This results in a space complexity of O, n, where n is the number of nodes in the sublist. Additionally, the traversal and reversal steps together contribute to a time complexity of O, n. The trade-off here is that although it's easy to implement, the extra space usage makes it less efficient for larger datasets. Another method is the optimized in-place reversal approach, which we'll explore further. The in-place reversal approach takes a more efficient route by reversing the nodes directly within the linked list structure, eliminating the need to extract or store the sublist separately. To implement this, we first locate the node just before the left position, which we call previous. Using three pointers, previous, cur, and next, we then reverse the nodes between left and right. These pointers allow us to carefully rearrange the links during the reversal process. Once the sublist is reversed, we reconnect it to the nodes before the left position and after the right position to restore the entire list structure. This process achieves a time complexity of O, n, as we traverse the list once and perform the reversal in a single pass. Additionally, it has a space complexity of O, 1, since no extra data structures are used. While this approach is slightly more complex to implement due to the intricate pointer manipulations, it is highly efficient. A third method we considered is the recursive approach, which involves reversing the sublist during the recursion's unwinding phase. However, recursion introduces a space complexity of O, n, due to the stack usage, making it less desirable for large inputs. Among the approaches considered, the in-place reversal method stands out as the most efficient in terms of both time and space complexity. The core idea is to reverse the sublist directly within the linked list, leveraging a three-pointer technique to manage the reversal process. This eliminates the need for additional storage, making the solution well-suited for large linked lists. One key observation here is that since reversing the sublist is a localized operation, it doesn't require extracting the nodes into a separate structure. Instead, careful pointer manipulation allows us to achieve the reversal in constant space. This strategy was chosen because it strikes the right balance between efficiency and practicality. While the brute force approach suffers from higher space requirements and the recursive approach risks stack overflow, the in-place reversal method avoids both of these issues. Although it demands more precision during implementation, it is robust and scales seamlessly with larger input sizes, making it the optimal solution. Despite its advantages, the in-place reversal approach does come with some trade-offs. The primary challenge lies in the careful management of pointers, which can be error-prone if not implemented correctly. This makes the approach slightly less intuitive for beginners compared to the brute force method, which is more straightforward conceptually but less efficient. However, the performance benefits of the in-place method far outweigh these drawbacks. By reducing space complexity to O(1) and maintaining a time complexity of O(n), it offers a solution that is both practical and high-performing. In summary, the in-place reversal approach is the best choice for this problem due to its optimal use of resources and ability to handle larger linked lists effectively. While it requires some attention to detail during implementation, its efficiency and scalability make it the ideal strategy for reversing a sublist within a linked list. To begin, we are tasked with reversing a portion of a singly linked list between two given positions, left and right. These positions use 1-based indexing, which means the first node is at position 1. The constraints ensure that the positions are valid, specifically that left is less than or equal to right and both are within the bounds of the list's length. The approach we'll use is an iterative, in-place method that focuses on manipulating pointers directly, which avoids the overhead of extra memory usage. First, we handle edge cases. If the list is empty, or if it contains only one node, there's no reversal needed, so we simply return the original list. Similarly, if left equals right, the sublist includes only one node, so no action is necessary, and we return the list as is. These checks ensure that we handle simple scenarios efficiently before proceeding to the main logic of the algorithm. Now, we set up the pointers needed for the reversal process. To simplify edge cases, such as when the sublist starts at the head of the list, we create a dummy node that points to the head of the original list. This dummy node acts as a placeholder before the start of the list, making pointer manipulations easier. Next, we initialize a pointer called previous and position it just before the start of the sublist to be reversed. To do this, we start previous at the dummy node and move it forward left 1 times. This ensures that previous stops at the node immediately before the sublist's starting position. Once previous is in place, we identify the bounds of the sublist using 2 additional pointers, start and then. The start pointer marks the first node of the sublist to be reversed, which is the node at position left, while then points to the node immediately after start, at position left +1. These pointers are key to isolating and reversing the sublist in the next steps. Next, we move into the core logic of the algorithm, which is the actual reversal of the sublist. This is achieved through an iterative process that runs right-left times, corresponding to the number of nodes in the sublist to be reversed. During each iteration, we adjust the pointers to reverse the order of the nodes. Specifically, we first update start.next to point to then.next, effectively removing the then node from its current position. Then, we insert then at the front of the reversed sublist by setting then.next to prev.next and updating prev.next to point to then. Finally, we move the then pointer forward by setting it to start.next, preparing it for the next iteration. These steps ensure that each node in the sublist is repositioned correctly, and by the end of the loop, the entire sublist is reversed. At this point, the reversed sublist is seamlessly reconnected to the rest of the list, with the order of nodes outside the reversal range remaining unchanged. Once this process is complete, we return dummy.next as the new head of the updated list. Reflecting on the algorithm, there are a few key insights to highlight. First, the use of a dummy node simplifies edge cases, especially when the reversal starts at the very beginning of the list. This avoids the need for additional conditional checks and makes the relinking process more straightforward. Second, the in-place reversal approach is highly efficient, as it directly manipulates the next pointers of the linked list without requiring extra memory for auxiliary data structures, resulting in an O(1) space complexity. Lastly, the careful movement of pointers ensures that each node is repositioned correctly and efficiently within the reversed segment. In terms of data structures, we work directly with the singly linked list nodes and their next pointers. The dummy node is the only additional structure introduced, but it simplifies the algorithm significantly. For complexity analysis, the time complexity is O(n), as we traverse the list once to reach the left position and then perform right-left iterations to reverse the sublist. The space complexity is O(1), as no extra memory is used beyond the pointers. Let's walk through a concrete example to see the algorithm in action. Suppose the input list is 1, 2, 3, 4, 5, with left equal to 2 and right equal to 4. Initially, the list looks like this: 1-2-3-4-5. We introduce a dummy node, which points to the head, resulting in -1-1-2-3-4-5. The previous pointer starts at the dummy node and moves to the node just before position left, which is node 1 in this case. Now, we identify the sublist bounds: start points to node 2, and then points to node 3. In the first reversal step, we update start.next to point to node 4, then .next to point to node 2, and prev.next to point to node 3. The list now looks like -1-1-3-2-4-5. Moving then to node 4, we repeat the process. This time, start.next is updated to point to node 5, then .next to point to node 3, and prev.next to point to node 4. The final list becomes -1-1-4-3-2-5. Removing the dummy node, the output is 1-4-3-2-5, which is the reversed sublist integrated back into the original list. Here, we begin by defining the node structure for our linked list using the listNode class. Each node contains a value and a pointer to the next node. Then, within the solution class, we define the reverse between function, which will handle the task of reversing a portion of the linked list between two specified positions, left and right. First, we handle the base cases. If the list is empty or if left and right are the same, there is nothing to reverse, so we simply return the head as is. Next, we introduce a dummy node. This is a common technique to simplify edge cases, especially when the reversal starts at the head of the list. The dummy node points to the head of the original list, and we initialize a previous pointer to this dummy node. The first step of the algorithm is to move the previous pointer to the node just before the left position. This is done using a loop that iterates left 1 times, advancing previous one node at a time. Once previous is correctly positioned, we prepare for the reversal by identifying 2 key pointers: start, which points to the first node of the sublist to be reversed, and then, which points to the node immediately after start. These pointers will help us in the actual reversal process. Now, the core of the reversal begins. We use a loop that runs 4 right-left iterations, effectively reversing the sublist 1 node at a time. Inside the loop, the first step is to adjust the start node's next pointer to skip the then node, effectively detaching then from its original position. Next, we insert then at the beginning of the reverse section by updating its next pointer to point to previous.next, which is the current head of the reversed sublist. We then update previous.next to point to then, making then the new head of the reversed sublist. Finally, we move the then pointer to the next node to be reversed by setting it to start.next. This process continues until the entire sublist from left to right is reversed. After the loop completes, we return the modified list starting from dummy.next, which points to the new head of the list. This approach ensures that we handle all edge cases, including reversing at the head or tail of the list, in a clean and efficient manner. Here, we start by defining a basic listNode class to represent the nodes of our linked list. Each node contains an integer value, val, and a reference to the next node, next. We also provide constructors to initialize nodes with or without a reference to the next node. Now, in the solution class, we define the reverse between method, which will reverse a portion of the linked list between positions left and right. First, we handle the base case. If the list is empty or no reversal is needed because left equals right, we simply return the head of the list as is. Next, we create a dummy node with a value of 0 and point it next to the head of the list. This dummy node simplifies handling edge cases, such as when the reversal starts at the head of the list. We also initialize a previous pointer to the dummy node, which will help us locate the node just before the left position. Next, we move the previous pointer to the node right before the left position using a simple for loop. This ensures that previous is positioned correctly to manage the reversal process. Once we've positioned previously, we set up two pointers, start, which points to the node at the left position, and then, which points to the node immediately after start. These pointers will help us reverse the sublist. We then use a loop to reverse the sublist one node at a time. Inside the loop, we detach the then node from the sublist by updating start.next, then insert then at the beginning of the reversed portion by adjusting its next pointer to point to the node currently at prevNext. We update prevNext to point to then, effectively making it the new head of the reversed sublist. Finally, we advance the then pointer to the next node to be reversed. After completing the reversal, we return the modified list starting from dummy.next, which represents the new head of the list. To solve this problem, we begin by creating a dummy node with a value of 0 and linking it to the head of the input list. This dummy node acts as a placeholder, simplifying edge cases where the sublist starts at the head of the list. Next, we initialize a pointer called previous and set it to the dummy node. The goal is to move previous to the node just before the position left. Since left is 2 in this example, we only need to move previous one step forward, so it points to the node with the value 1. At this point, we've set up the initial state to start reversing the sublist. Now, we proceed to reverse the sublist between positions left and right. First, we identify the starting point of the sublist by setting start to previous.next, which is the node with the value 2. We also initialize a pointer then to start.next, which is the node with the value 3. Since the difference between right and left is 2, we need to perform 2 iterations to reverse the sublist. In the first iteration, we update start.next to skip the node then is pointing to, effectively connecting it to the next node in the list, which is the node with the value 4. Then, we insert then at the beginning of the reversed portion by updating then.next to point to previous.next, and adjust previous.next to point to then. Finally, we move then forward to the node with the value 4. In the second iteration, we repeat this process, adjust the links such that start.next skips the node with value 4, then .next points back to the reversed portion, and previous.next points to then. After these updates, then moves to the node with value 5, and the sublist is now reversed. The result at this stage is the list 1, 4, 3, 2, 5. In the second example, we're reversing a sublist that starts at the head of the list. Here, the input list is 3, 5, and the positions left and right are 1 and 2, respectively. We start by creating a dummy node with a value of 0 and linking it to the head, as before. The previous pointer is initialized to the dummy node. Since left 1 equals 0, previous remains at the dummy node. Now, we identify the sublist to reverse. Start is set to previous.next, which is the node with the value 3, and then is set to start.next, the node with the value 5. Since right left is 1, we have only one iteration to reverse the sublist. During this iteration, we update start.next to skip then and point to then.next, which is none. Then.next is updated to point to previous.next, effectively inserting it at the beginning of the reversed portion. Finally, previous.next is updated to point to then, and we move then to start.next, which is now none. The resulting list after this operation is 5, 3. Finally, let's consider an example where no reversal is required. Here, the input list is 1, 2, 3, 4, 5, and left and right are both 3. In this case, the base condition left equals right is true, indicating that the sublist to be reversed contains only one node. Since there's no need for any changes, we simply return the original list as is. The output in this case remains 1, 2, 3, 4, 5. This highlights how the algorithm handles cases where no action is needed, optimizing performance by avoiding unnecessary operations. The time complexity of the reverse between function is O(n), where n is the number of nodes in the linked list. Let's break this down into its key steps. First, we move the previous pointer to the node just before the left position. This is achieved through a loop that runs left 1 iterations. In the worst-case scenario, when left equals n, this loop will execute n iterations. Next, we reverse the sublist from position left to right. This process involves relinking the nodes within the specified range. The loop here runs right-left iterations, which corresponds to the size of the sublist being reversed. If the entire list is reversed, such as when left equals 1 and right equals n, this step will also require n iterations. Now, combining these steps, we can see that the two loops execute sequentially. This means the time complexities are additive, resulting in left 1 plus right left. Simplifying further, the overall time complexity is n, as the total number of iterations is always bounded by the size of the list. Shifting our focus to space complexity, the reverse between function operates in O1 space because it modifies the linked list in place without requiring additional data structures. This is achieved by directly adjusting the next pointers of the nodes in the sublist being reversed. Additionally, the algorithm only uses a constant number of pointers, such as dummy, previous, start, and then. Regardless of the size of the linked list, the memory consumption remains constant, confirming a space complexity of O1. When comparing to a naive or brute force approach, the differences become clear. A naive solution might involve copying the linked list nodes into an array, reversing the sublist within the array, and then reconstructing the linked list. This would require a time complexity of n for traversal, right-left, for reversing the sublist, and another n for reconstructing the list, resulting in an overall time complexity of n. However, the space complexity of this approach would be n, due to the temporary array required. In contrast, our current solution achieves the same n time complexity but is significantly more space efficient at 1. Furthermore, analyzing the best, average, and worst cases reveals that the time complexity remains n in all scenarios. For example, if left equals right, no reversal is needed, and the function simply traverses to position left. In the worst case, where the entire list is reversed, the complexity is still n. Finally, let's mathematically validate the big O analysis. The algorithm iterates over the list at most n times. This includes left 1 iterations for the first loop and right-left iterations for the second loop. Adding these together gives a total of n iterations. Since big O notation captures the asymptotic upper bound, the overall time complexity is n. As for space complexity, the algorithm uses only a constant amount of memory, as no additional data structures are allocated beyond the pointers used for manipulation. This confirms that the space complexity remains 1. When working on this problem, there are a few common mistakes to watch out for. First, if the left and right positions are the same, the sublist to reverse consists of just one node. In such cases, there's no need to perform any operations, simply return the head as is. Not handling this can lead to unnecessary computations or even errors. Next, while reversing the sublist, it's crucial to update the next pointers correctly. Missing any step in the pointer adjustments can cause the linked list to break or even form cycles, which would invalidate the structure. Additionally, once the sublist is reversed, you must relink it to the rest of the list. This means reconnecting the reversed portion with the nodes before left and after right. Forgetting this step can leave parts of the list disconnected. Finally, remember that linked list problems often use one-based indexing for positions like left and right. If you accidentally use zero-based indexing, which is common in arrays, it can lead to off-by-one errors and bugs in your solution. Another important consideration is how you handle edge cases when modifying the input list. For example, if the left position is 1, reversing the sublist will change the head of the list. In such cases, you need to ensure the head pointer is updated correctly. Now, from an interview perspective, this problem is often used to test how well you understand constraints and edge cases. You might be asked to handle scenarios like reversing the entire list, reversing a single node, or reversing when left and right are at the very beginning or end of the list. It's also a test of your ability to manipulate pointers within a linked list, a skill that requires careful visualization to avoid mistakes. Lastly, interviewers typically value efficient solutions, so make sure to highlight that your approach works in n time with 1 space, as this is the optimal solution for this problem. A key aspect of solving this problem in an interview is explaining your thought process clearly. Walk through how you identify the sublist to reverse it step by step, and then reconnect it to the rest of the list. Clear articulation of these steps is just as important as writing the code itself. If you're looking to build a stronger foundation, related problems can help reinforce your understanding. For instance, LeetCode 206, Reverse Linked List, is a great starting point for practicing full list reversal. LeetCode 25, Reverse Nodes in K-Group, extends this concept by focusing on reversing nodes in fixed-sized groups. Another interesting problem is LeetCode 1721, Swapping Nodes in a Linked List, which involves pointer manipulation to swap specific positions. Finally, LeetCode 234, Palindrome Linked List, requires reversing part of the list to check for symmetry, providing another opportunity to practice these techniques. There are also alternative approaches you should be aware of. One option is to solve this problem recursively. While a recursive solution can work, it's generally harder to debug and less intuitive compared to the iterative approach. It also requires extra space for the recursion stack, which can be a disadvantage. Another alternative is to copy the sublist into an array, reverse the array, and then copy the values back into the linked list. This method is straightforward and easy to implement, but it uses extra space, making it less efficient. Finally, for smaller linked lists, a two-pointer approach can be used to manually identify and reverse the nodes. While this method might be simpler in concept, it doesn't scale well for larger lists, so it's not ideal for general use. Understanding these alternatives can deepen your insight into the problem and prepare you for variations you might encounter in interviews. Great job! We explored how to reverse a sublist in a linked list, using an efficient in-place algorithm. Remember, mastering linked list manipulation is a valuable skill for technical interviews. Keep practicing, and don't forget to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!